A pleasant morning to everyone gathered here. Coming together is beginning, keeping together is a progress, and working together is a success. Novelty for us is excitement and exuberance, surprise and science, positiveness and patience. Words are rose petals that are sprinkled with fragrance to invite one and all present here with a warm greetings. We, the Universal Intellectual Trust family, at our National Virtual Conference on Sustainable Chemistry and Renewable Energy 2022. On behalf of Universal Intellectual Trust, we warmly welcome all of you. First and foremost, I would like to thank everyone taking time off your busy schedule to join us today. We hope you learned today a lot. We have lined up for you to be fruitful and engaging. It is rightly said, flowers can't blossom without sunshine, and man cannot live without love. As like us, conference can't start without the hearty welcome. We invite our greeter, Dr. A.S. Ganesh Raja, Chairman of Universal Intellectual Trust, to spray the sweet aroma of happiness through the words of welcome.
Thank you, Soundarya. Good morning to everyone present here. On behalf of EIT team, I am glad to welcoming you all to the second day of National Virtual Conference on Sustainable Chemistry and Renewable Energy, organized by Universal Intellectual Trust, Viluppuram, Tamil Nadu. Our UIT takes essential steps for creating the intellectual peoples using various advanced tools of modern educations with research-related science and technology, thereby creating social awareness necessary for establishing a healthy society. In this great manner, UIT initiates some scientific activities for our society with service-minded persons. Here, I like to show some of our scientific activities going on in EIT teams. Our secretary introduced our EIT team. So I go to EIT. Still now finished 12 webinar series with experts. We have to finish the EIT EQs with prizes. This block we have to publish many scientific e-contents. We already published more than 100 e-contents in this forum. We are also calling scientific experts talks. In this as well as books, we currently we called books entitled of Nanomaterial Photocatalyst in energy and environmental applications with ISBN number and Scopus status. Welcome you, sir.
Invite our chairperson. Success is not final. Failure is not fatal. It's the courage to continue that counts. Now, I invite our chairperson, Dr. Saravanan Pichai, Associate Professor in Indian Institute of Technology at Jharkhand.
Thank you, Ms. Kausalya. So, good morning to one and all. So, I'd like to take this opportunity to introduce today's first plenary speaker, Professor Venkataraman. So, Professor Venkataraman is currently a professor in Indian Institute of Science and Education Research in Kolkata. He has held many various positions in the same institute since 2009 until now. So currently, he is serving as a professor, a successful chemist, and graduated with PhD in chemistry from IIT Madras in 2001. And he has actually quite a decade experience as a postdoc from Trinity University, University of Victoria, Canada, and Concordia University, Canada. So then actually his research interest is focused on mostly on functional materials, that is energy materials. So like layered nanostructures for a supercapacitor application and colloidal emissive nanocrystals for sensing and light application. He also extended his work to work on the environment remediations with photocatalysis, CO2 conversion, etc. So to his actually to till date for more than 2 decades, he has more than 100 publications with an H index of Google H index of 29. And the citations of more than 4,000 plus. So he has an accomplishment of grant, that is an external grant, close to 1.5 crores from either from CSIR and from DST in the field of that energy storage application. Most of his grants are actually is operating on energy storage applications, and has graduated 9 PhD and graduating 10 more in his actually as a thesis advisor. So with this introduction, so I now introduce Professor Venkataraman to continue his plenary talk on the topic of on the topic of development of transition metal based nanostructured materials for energy application for next 1 hour. So Professor, please take over.
Yeah, thank you, Professor Saravanan Pichai. Thank you for a very kind introduction, and I'm very much pleased, and thank you so much for this. And also at the outset, I would like to thank the organizers, Dr. Rajkumar and Dr. Ganesh Raja and Dr. Chandrasekhar for giving this wonderful opportunity, as well as running this trust, particularly helping students and researchers and enriching them with the science and knowledge. So, which is very important, and it has a really societal benefit. And I wish to continue. I wish them all the best to continue the same. And I would like to definitely, at any point in time, if I will be of any help, I will be very happy to do that. Today, I'll be talking on the transition metal development of transition metal based nanostructure materials for energy applications. So. Much of this introduction to today's talk is already very nicely presented by Dr. Gopinath yesterday, particularly on need of sustainable energy fuels. Also very nice presentation by Dr. Saravanan Pichai on the photocatalysis, and also very important topic he touched on, the water purification. See, without water we cannot live today. Water is very important for us, and today I'm going to say something. Water can be useful for energy as well. So this talk, so I will not give a much introduction to this topic. So our research interest mainly, as mentioned by Dr. Saravanan Pichai, is on, yeah. So mostly initially we were working on lanthanide bright luminescent nanocrystals, basically mostly on upconverting nanocrystal, and trying to explore them for LED application, light emitting application. And we worked on photocatalysis, not really much, I should say, not like Professor Saravanan Pichai explored photocatalysis to the extent and is continuing to do, but we try to do the visible and NIR combination of photocatalysis to some extent we did, and because that interest came from that upconversion property of the lanthanide ions, and mostly we worked on the detection of toxic metal ions. So we have a series of papers on this one, mainly on lead, mercury, iron, copper. So, and small molecules like melamine. So then we started almost like 4 or 5 years back. We started working on these two topics, like CO2 and conversion into value-added chemicals. Mostly we developed catalyst for epoxide to cyclic carbonates, and we try to do on atmospheric pressure. So most of the studies in this field is working on high pressure. So we try to see whether we will be able to do it at atmospheric pressure. Of course, the temperature is a little higher. So we are now trying to see that how we can balance these two, so that we will be one day able to prepare something at room temperature as well as atmospheric pressure. So, and then we were working on this electro catalysis mainly, and energy storage, as you said, for supercapacitor applications. But today's talk, I mostly concentrate on the electro catalysis and mainly on hydrogen evolution and oxygen evolution reactions. So this is the content of my talk with a short introduction to renewable energy. I'll go to the work directly on 2D nanostructured materials, how transition metal dichalcogenate for hydrogen evolution, and mostly nickel and oxide cobalt based catalyst used for water oxidation, that is oxygen evolution reaction. And if time permits, I will show one example of this heterostructure, interfacial structure, which can be used for alkaline hydrogen evolution reaction. Okay. So if you see the history of the fuels, so wood from very early centuries, wood was used as the major sources of the fuel. In the medieval Europe, wood was not only used for the construction, for domestic and industrial heating purpose, particularly for refining of ores. This led to the energy crisis, which we talk about today very early, much in the 16th centuries. And in fact, Britain ran out of wood in the 16th century. So this led to the lookout for alternative for wood. So coal came as a suitable substitute for wood as a fuel. So this transition from wood cutting to coal mining as a main source of heat was part of the early British economic revolution and 2 centuries later in the Industrial Revolution. Around in the 19th centuries or so, what we probably used carbon-based fuels, what we use today. So one of the major concern of use of carbon-based fossil fuels is the release of CO2 into the atmosphere and other toxic gases. In addition, we may run out of this source one day. So it's thus important, very important to develop alternative and sustainable energy sources. So let me go to, yeah. So what is the need of the, so although wind and solar energy are quite promising, they are very intermittent. So the success is depend on the couple, how efficiently you couple them and store them particularly. So you can store them by, for example, in batteries, fuel cells. These are some of the energy storage devices. So what we need to do is we have to generate that energy using this wind or like sunlight and then store them to later use. On the other hand, so hydrogen is a very promising and a clean energy carrier, as Dr. Gopinathan was explaining yesterday. It has a high specific energy of 142 megajoule per kilogram. So it's very zero emission fuel. So steam reforming is a well-known process today to produce hydrogen. However, it required a high temperature and pressure. So alternatively, electrochemical water splitting can be an efficient and sustainable approach for hydrogen production. So it can be produced through the renewable sources, like for example, wind or energy or solar, for example. So this water splitting basically to produce hydrogen is delta G positive, as Dr. Gopinathan was mentioning yesterday, like it needs 1.23 electron volt. Of course, the fuel consumption on the other hand is delta G negative. But if you see the thermodynamic energy requirement, the minimum amount of energy is around 232 kilojoule per mole. That is E naught. I was mentioning that E naught is equal to minus 1.23 volt. The energy of this standard terrestrial solar spectrum is about like 100 milliwatt per centimeter square. So that the current density at 100% solar to hydrogen conversion is roughly about 82 milliampere per centimeter square. So if you see the current density at 10% solar to hydrogen efficiency is roughly like 8.2. That will roughly take as a benchmark as 10 milliampere per centimeter square, which I'll be showing in my slides. But it's just a convention, like we take the benchmark as 10 milliampere per centimeter square. So suppose if you have 1% coverage with the 10% STH device, we will not need to worry about for next, so at least 2 to 3 decades. But the problem is status is roughly 1%, the present status. So what is the major problem? What is the problem in converting or getting hydrogen from water is the kinetic constraints. Okay, it involves multiple steps. It brings to high activation energy barrier, and the catalyst surface is needed to overcome this activation barrier. So that is the reason that we need a very good catalyst to produce hydrogen from water. If you see, so in general, the best thing is to do is you have to couple these two, that the solar light and then this energy conversion, energy generation and the chemical conversion, both steps. However, this water splitting is something very complicated process. So it needs, it has several activation barriers. That's why you have to decouple and work on both separately. And so here I show say this is the current density versus this voltage potential, and what we basically see is the catalyst, ruthenium oxide and iridium oxide are benchmark catalysts for the oxygen evolution reactions. So till date, they are very good for oxygen evolution reaction, but what you see is it always needs an extra potential from the thermodynamic potential to split water. On the other hand, in the hydrogen evolution reaction is relatively a 2-electron process, whereas oxygen evolution is a 4-electron process, as I mentioned here. Platinum is one of the best catalysts till today. But the problem is platinum is expensive. It's quite expensive. Also, their abundance is not very high. So it is very important. Same is true with ruthenium and iridium. They are expensive. So it is very important to develop catalysts which can match or can be better than platinum or ruthenium or iridium for oxygen evolution reaction, or platinum in the case of hydrogen evolution reaction. So this is a typical setup which is used to measure this activity, whatever that potential which we measure, or we call it as an over potential. That means the potential which is required extra to achieve this water splitting. Okay. So this is a typical 3-electrode setup. I think most of you are familiar, but not familiar with that. We have a working electrode, we have a reference electrode, and a counter electrode. So basically the platinum is used as a counter electrode. Working electrode is your catalyst, and the reference electrode mostly is AgCl taken. So you have connected with the potential stat, you applied potential and tried to change the electrode potential and see how the system reacts. And what you measure basically is that the over potential that is required to achieve this water splitting. So this is a typical cyclic water. So it's not a complete CV, it's a half of it. Okay. So what we generally measure is what is the potential, over potential needed to match 10 milliampere per centimeter square. Okay, so for example, if we have a 2 catalyst, one has this at 1.5, over potential is observed for 10 milliamp. Here it's given as a 10 milliampere per centimeter square. It requires 1.53 volt, and the other one requires 1.63 volt. Means this is a better catalyst. The green one is a better catalyst than the red one. So what we need to do today, research is in this direction, working on how to bring this very close to this one. So that is the challenge in this field, and particularly oxygen evolution is challenge. I will show you. This is briefly I will explain what is hydrogen evolution reaction mechanism. So it has an adsorption process, which is a proton coupled electron transfer process, where you can see that the hydronium ion, which on the metal, which is your catalyst, and you have an electron. So what would basically happens is that metal hydrogen gets adsorbed on the metal, and this happens in the acidic pH. In the base, what happens is with the water, and we have a metal, which is your catalyst, and then same reaction happens, and this is called Walmer step. But here is basically what is needed is the breaking of this water to H plus and OH, but in the case of acidic pH, you already have a hydronium ion. In the next step, basically there are 2 different mechanisms can happen. One is Hiroshiki mechanism, another is the Tafel step. So in the acidic medium, what happens, this adsorption, metal hydrogen adsorption, which is happening at the Walmer step, which combined with already existing H plus and E electron will give hydrogen gas, or in the alkali, it will have water, similar reaction with water. In the case of a Tafel step, what happens in both cases, with acidic as well as alkaline medium, the 2 metal hydrogen, which are nearby, combine, and that hydrogen combined to give hydrogen gas, and the metal will be released. This is a brief mechanism on hydrogen evolution reaction. But if you see the oxygen evolution reaction, which is the counter reaction, it's a little very complicated process. It's a complicated step because it involves 4 electron proton transfers. For example, if this is a metal, this is a metal which is a catalyst, and now what happens in the presence of water, there is an H plus and electron release, which leads to MOH. First, it forms an metal hydroxide, and this metal hydroxide can form metal oxide by again release of a proton and an electron. And again, this metal oxide can directly go to the metal by release of oxygen, or it can again react with water to form metal oxyhydroxide species. And then again with one more electron and the proton release, it will become metal. Again, the metal is released and oxygen is released. But predominantly, the 4-electron process here, basically, that metal oxide to oxyhydroxide formation is well known. So most of the cases it's observed and that has been proved as well. But this, in some cases, this metal oxygen directly goes to the releases oxygen, has been observed with some catalyst. But as you can see, this oxygen evolution mechanism involves a 4-electron proton transfer process. Therefore, and the kinetics of each process is very intricate. So the release of oxygen here depends on all 4 steps. So particularly that hydroxide oxide to oxyhydroxide formation, and particularly oxide to oxide, hydroxide to oxide formation, it depends on the pH and various things. So that is why this 4-electron process is a very challenging process. That's why a lot of work compared to hydrogen evolution reaction. There are more research reports on oxygen evolution reaction, how to develop a suitable catalyst which can do this oxygen evolution process efficiently. So there are various catalysts. As I mentioned before, that platinum is one of the best catalysts for hydrogen evolution reaction. Of course, molybdenum sulfide and other 2D transition metals, dichalcogenates like vanadium sulfide, tungsten sulfide are very good materials for hydrogen evolution reaction. On the other hand, for oxygen evolution reaction, mostly cobalt and nickel based materials are very effective. So for cobalt oxide, hydroxide, nickel cobalt oxide, like the spinal structures, and hydroxide, sulfides, there are various catalysts developed for this material. So what is very important, we have to make a material which can bring down the overpotential or very close to 1.234. So what they do is they combine this sometimes with the graphene and other carbon-based materials to improve the activity of the material. So today I'll show you some few examples which we have done in our group in the last 4-5 years on hydrogen evolution reaction and oxygen evolution reaction. This is the work where we have done this MOX2, that is sulfide and molybdenum sulfide and selenium based materials for hydrogen evolution reaction. So molybdenum sulfide is a very interesting material. It has a layer structure. If you see that the molybdenum and the yellow colors are the sulfur molecules. So the distance between these 2 layers is roughly 6.5, which is in the bulk. And what is very interesting is this interaction between them is through weak van der Waals interaction. One can actually tune these layer structures very effectively. But MOS2, particularly molybdenum sulfide and selenide, can exist in 2 different phases. For example, 2H phases, which is semiconductor, and the 1T phase, which is metallic. So the structure is slightly different for 2 of them. One is D3H symmetry, another is the octahedral symmetry. If you see, for example, it has 2 d electrons. So the splitting looks like this. So it basically have a very stable state compared to this one, because there is 1 electron less is in this state. So 2H phase is quite stable. So there are a lot of any synthesis which you do, mostly you end up in a 2H phase, which is semiconductor in nature, but the activity of the 2H is very less compared to the 1T phase. 1T phase is more metallic, so more conducting, and the activity is better. However, stabilizing 1T is very challenging. So it's not very easy. So always, even if you prepare, always they exist together with the 2H phase. So what I said, the rest of the talk is 1T means it has some contribution from 2H as well, particularly on colloidal synthesis. If you make a thin film of MOX2, Then you can prepare pure 1T phase material, which has several applications, particle field effect transistors, and also they are very good material for hydrogen evolution reaction, and they have shown excellent activity for thin film based material. However, in the colloidal synthesis, it's very difficult and challenging to prepare. So that's why we wanted to see how we can make, whether we can make 1T phase. So our idea is to achieve this 1T phase. And there are reports that small molecule intercalation into the MOX2 layers, that in between the layers can increase the distance, that turns or that creates 1T phase in the material. So we thought, why don't we have ionic liquid inside the materials, and we synthesize this using this simple hydrothermal setup where we have taken sodium molybdate thioacetylide as the sulfur source, and we have taken simple bromine like ionic liquid, and we try to do directly deposit the material on the carbon cloth. The reason is that if you prepare and then later you do, then you need some kind of a binder to do that, will create like some resistance. So we thought, if we are able to prepare this directly on the carbon cloth. So what we do is we put the carbon cloth during the reaction, so there's an in situ growth of this MOS2 occurs. So you can clearly see that this is the carbon cloth. After the reaction, you see that the black precipitate or Wattler product that is deposited on the substrate. So to understand whether it is 1T and 2T, I'll come to the characterization, which is again a tricky part. But what we do is we anneal them and to get the 2H phase. When we anneal at higher temperature, it is converted into a MOS2 as a 2H phase. These two are on the carbon cloth. So I will compare the results with the not directly, that is grown substrate, which is deposited on the carbon cloth for comparison. How efficient would be that if we directly grow them on the surface. So this is the XRD pattern of this material MOS2 1T phase, which is like with the ionic liquid intercalated compound, and you can see that the 2H phase there, you can clearly see the 10-degree peak, that is 14-degree peak, which is in the bulk. 002 plane peak, which shifts to the lower 2 theta value. That tells that there is an increase in the layer distance very clearly. And this is supported by the Raman measurement, where you can see that the 2H phase, these are characteristic peaks of this E12G and A12G peak are characteristic for the 2H phase. Whereas for the 1T, what we observe is the extra peaks which you will see for only the 1T phase. So this clearly confirms there is a formation of 1T phase. However, there will be some portion of that will contain the 2H phase as well. So this is a morphological study using scanning electron microscopy, some images of these materials, and I have shown this how they are grown on the carbon cloth. This is similarly 2H. There is not really much difference between the 2H 1T and the 2H phase, but this is a direct powder. You can see that the powder how they are looking like, but when they grow on these sheets, they grow like a flowers. Okay, so you can actually do a TREM analysis to find out the layer distance, which I was talking about. There is an increase in the layer distance is confirmed by the high resolution transmission electron microscopy, where you can see that there is an increase in the distance from 0.65 and to almost like 1.07 nanometer. So there is an increase in the layer distance upon incorporating this ionic liquid inside the material. Okay, this is further confirmed by the XPS, where you can see that the 1T phase has like a slight shift in the peak, which is caused by the 1T. Basically, on the peak fitting, we found there is some contribution from the 1T phase of the material and along with the 2H phase. So as I mentioned before, that always 2H phase coexist with the 1T phase. And here I have shown the hydrogen evolution reaction. What we show is a simple cycle to voltammetric peak, but we have shown only the backward scan of this one part of it. So here I have compared the 1T phase with the 2H phase, and as I mentioned before, platinum is something here. So what we need to do is we have to bring close to this curve, very close to the platinum. So here you can see that the black 1T phase, which shows a much lower potential, what we measure is an over potential compared to the 2H phase and to the directly measured one. Even they are not able to achieve this 10 milliampere per centimeter square. But what we can see here, that the 1T phase, which shows a better activity, this is also reflected in the Tafel slope, where the overpotential is plotted against the log current density. What this value means is basically how much of overpotential needed to increase the current density by 10 times. Okay, this is one of the features which we measure characteristic of this material to relate to other materials. So you can see that the 1T phase material shows only 68 millivolt per diode, whereas the other material shows higher value. So continuing on this, we thought, is there a only way, like putting organic inside them? It's not a very good idea. So we thought, is there any other way to do this one? And then we come up with an idea that chromium doping will help. Because chromium again can have one more electron which can fill in that 2 to G. I hope you remember that in the octahedral symmetry we have one electron less in the lower orbital, T to G orbital. So if we have chromium inside this material, this time we took MoSC2. This, of course, we have done the similar thing on MoS2, but the results were better for the MoSC2. So that's why I'm showing this with the MO1T phase of MoSC2 on this. This is again prepared through the hydrothermal method, and what we do is we compare without and with the chromium the results. So here you can see that the 1T phase and the 2H phase, what we see is the 002 plane here, it's basically little vanishing. That means the material is more amorphous. This is what you see, very thin, very few layers of MoSC2 can be obtained by this method. And here you see that the peak for this 002 plane, which gives the interlayer distance idea. And here again, you can see that the 2H phase and 1T phase, we have like more peaks compared to the 2H phase, but along with the 2H phase. So 1T is present along with the 2H phase. So as I mentioned before, that is very difficult to prepare pure 1T phase. It's still a challenging one. So here I show the result. Here I have given the PTC carbon for comparison. This is how. So basically you need to reach this. But as you can see here, we have varied the chromium amount to see which one is showing the best activity. And what we found is the chromium, 2% doped chromium shows better activity compared to other samples. Basically, upon increasing, of course, 1 shows better, slightly better, 3 shows slightly better, but later after 5, the activity again decreases. So 2% is the optimized concentration of chromium doping inside the MoSC2, which shows better activity. Here I have plotted the overpotential with all these samples. As you can see that the 2% doped chromium, which shows 176 millivolt in acidic pH, and compared to other materials. So this is also reflected in the Tafel slope, where you can see 77. This is for the PTC. Okay, so it's very close to PTC, but other values are much higher. So this is for the 2% doped chromium sample, which is also supported by the impedance measurements. What we do in impedance measurement gives idea about the solution resistance as well as the charge transfer characteristic of the material. But what we can see this that hump, which is the semicircle, which is very small for the 2% doped chromium, shows that there is a resistance is very less in this sample compared to for conductivity for the electron to reach, or the to reach the OH minus to reach, or H plus to reach the electrode. Okay, so compared to other samples. Okay, so what we see is here is the double layer capacitance, which we measure as another characteristics which we tells about electrochemically active surface area, which has a higher surface area, means that activity is generally better. Okay, so here you can see that the 2% doped chromium sample shows a higher double layer capacitance compared to all other samples. Okay, and this is to understand how much of 1T phase is present inside the material. We have done from the XPS analysis. As I mentioned before, like XPS is one of the tool to understand this 1T and 2T phase. And what we observed is we get a higher 1T phase content, about 50% or slightly more than 50% of 1T content in the case of 2 2% doped chromium compared to 3 and 5% chromium. Compared to pristine is quite high. Okay? So that means without chromium sample. And we then try to understand what is the reason why this chromium doping is helping in the increasing the activity of the hydrogen evolution reaction. We have done the DFT calculations which reveal that the increased room temperature charge density of MOSE2 monolayer through chromium doping. What we can see here is basically the band gap decreases. You see the band gap compared to this. This is the chromium sample that we can see that the band gap decreases. Also the Fermi level becomes close to the conduction band. That means that there is an increase in the metallicity, which increases the conductivity, which is good for the catalytic process. So I think in the rest of the talk, I will concentrate on mostly catalysts which are used for oxygen evolution reaction. Okay, as I mentioned before, it's quite challenging compared to hydrogen evolution reaction. So we try to prepare nanowire. The idea here is suppose how to increase the surface area of this catalyst so that several catalytic active sites can be present on the surface of the material. With this idea, we try to prepare this nickel iron nanowires. So what we have done briefly, the synthesis is quite simple. So what you take is the nickel chloride with the ethylene glycol, which is a structure directing agent. And we mixed this at 110 degrees centigrade to hydrogen hydride in the presence of iron chloride. Okay, what we get is the nickel iron nanowires, which I will show the images soon. And then what to activate or to make these nanowires active, what we do is we do them and drop cast them on the carbon paper and perform chronoamperometry. That is, we apply potential for a very short time, 120 seconds, 20 CV cycles to get them deposited on the nickel iron oxide hydroxides, okay, which are like better catalytic activity compared to the nanowire metal alone. So for comparison, we have made only the nickel wires and the same experimental procedure. So what we see is the XRD pattern clearly confirms the presence of iron nickel nanowires. And with the increase in the iron content, for example, if you take that iron content 1.2, what we see is we started to see the peaks corresponding to iron hydroxide. So we felt 1:1 is one of the sample which is showing like a pure nickel phase, and we optimize and use them for further characterization. And what we see in the SEM images is basically you see a beautiful nanowires of this with some protrusions on the surface, which is very clear from the TEM images. You can see them some kind of a protrusions at the surface. This is first time we are observing something interesting on the surface. But what we see is kind of like a very crystalline material on this one. Maybe the XPS indicate that there is a small amount of nickel oxide that is present on the surface. Okay, so then we try to understand why there is nanowire formation happen. We try to do this time-dependent morphological analysis where we can see the reaction at different times, and what we see is we obtained at the 0 time. They look like very aggregated particles, no particular shape or so. After 1 minute, similar. After 2 minutes, again aggregation. 3 minutes, we started to see something like kind of some little longer protrusions, and what we see after 6 minutes is something like a nanowire formation happens. So this happens quite fast, but we were able to do this time study, and this is also supported by the uniform distribution of these metals on the surfaces by the IDAX mapping. And also we have done the XPS to characterize any other phases are present, like you can see the two chemicals to understand the chemical state of the material. And we found that the nickel is present, and the presence of nickel is there, and there is a small amount of nickel oxide formation is also there. Okay, this is for the iron XPS. So it shows that the presence of iron because we wanted to confirm that the iron is present in the material. So this is the electrocatalytic activity where we can see only the backward scan. Okay, so that we can divide off any capacitance contribution. So this is the real contribution for the activity. And we have here compared ruthenium oxide, as I said, is one of the benchmark catalysts for the oxygen evolution reaction. And this is for the nanowire, nickel nanowire. This is nickel, and this is nickel iron. And you can see for different ratios, we have done 1:1, 2:1, and of course 1:1 is the optimized structure, and only the carbon paper. So we can see that this is the ruthenium oxide value, which is again better. But next to this is the nickel iron 1:1 nanowires. So here I can compare that how without iron and with iron, there's an increase in the decrease in the overpotential for the oxygen evolution reaction. So this is the overpotential graph for various things at different current densities. As I said, this 10 mark is generally taken as a 10 milliampere per centimeter square, but it is not really very appropriate, I should say. Now say we have done with the 50 milliamps also, how much extra potential that is needed, overpotential is needed to reach 50 milliamp per centimeter square. And what we to understand whether why there is an increase in the activity for nickel iron compared to only nickel wires, we have done the capacitance as well, like electrochemically active surface area through CDL measurements. And what we see here is interesting. You can see here the overpotential is better for the nickel iron 1:1 nanowires, whereas here there is a high surface area found for nickel, though the nickel activity is very less here, high overpotential. So this basically indicates that it is not the surface area, number of the catalytic active surface present on surface is the intrinsic activity. So basically iron increases the intrinsic activity of the nickel for the oxygen evolution reaction, which is well known. Of course, the mechanism has a lot of debate, but still iron improves the activity of the nickel for the electrochemical surface. This is very clear from this data. So then we try to understand whether iron is present in only at the surface or at the core, which acts to improve the activity of this sample. What we have done is we have done the iron spiked nickel wire. That means we taken the nickel wire and the electrolyte, slowly we spike different concentration of the iron into it. Okay, and see how does the activity improve. And here I have compared with the pure nickel, as mentioned, and as you can see that the different concentrations of this iron spike at different ratios of nickel to iron, what we see is the nickel iron shows a better activity, and for different spike sample it increases basically. Okay, so this basically tells that the activity is still this activity of nickel iron nanowire which we prepared previously is better than this activity. That clearly indicate that there is this nickel is not only iron is not only present in the surface of these nanowires, but also present at the core of these structures. Okay, this is the before and after catalytic activity. So the reason we do this morphological or other characteristics studies after post electrochemical activity, this is because what happens is sometimes this the activity, the improvement is due to the change in the structure or change in the morphology of this, or it's a surface area, many parameters change. So the actual catalyst acts as a pre-catalyst, which I will show some examples, very interesting examples later. But to understand that whether any nanoparticle, the nanowire morphology modifies or changes or not, we have done the TEM studies, and what we found is it's not really changed. That nanowire is slightly roughened, but basically the morphology is retained. What we see from the TEM is slight and amorphous layer formation that happens on the nickel wire surface, which is good, which is the active, which basically improves the activity. For catalysis, amorphous layer is something very important. They show that better activity compared to the crystalline material, and this is due to the formation of nickel oxyhydroxide, which happened during the oxidation process. So this nickel oxyhydroxide formation is necessary for the improved catalytic activity. Okay, so I think now how much time I have? Like I will try to. I still have.
Yeah, you have 20 minutes left.
Okay, sure. Thank you so much. So the next, what I will show an example of like a bifunctional catalyst with the nickel, cobalt, and molybdenum hydroxide. The reason we have taken this, and particularly we wanted to do this on directly on the copper mesh instead of like most of the studies are nickel mesh, which is quite expensive. We thought if related to copper mass. We thought if you do the copper mass, we take and directly deposit, and particularly we wanted to develop most of the nickel, cobalt based materials are made by hydrothermal route. So we thought if we can make something very at a lower temperature, simple process, this can be which can be extendable and scalable. This is the idea we had with which we have done this copper mesh study, but we have taken these three metal. I'll tell you why, that we wanted to understand the each component, how this nickel, molybdenum and cobalt improves the activity, particularly for the bifunctional activity. That means a catalyst which you use for both hydrogen evolution as well as oxygen evolution material. So what we have done is we have coated this material on the copper mesh, and we did this precondition study as I mentioned before. And what we observed interesting is the molybdenum leaching that happens during this electrochemical precondition study. I'll explain why molybdenum leaching is important here. So what we have done, this is a simple setup, that setup schematic of this setup, where we have taken this copper mesh and reacted with this is the equation how this urea combination results in this ammonia production, which is helpful for the metal hydroxides. So initially the metal hydroxide carbonates are formed, later it will be transferred at higher temperature to the hydroxides. Okay, so this is a simple reagent battle heated at 90 degrees centigrade, as I mentioned. To understand what we have done is we have taken the various ratios of this, whatever combinations possible, to understand which is the best optimized sample. We have done only nickel, cobalt, molybdenum, and then nickel, cobalt, and nickel, cobalt, molybdenum, everything into different ratios. Okay, it's a very simple setup, just changing the concentration of that. And I'm showing some of the images, transmission electron microscopic images of this material like nickel, cobalt 2. And you can see when we have nickel and cobalt, you have a rod-like structure. But when you have nickel and molybdenum, you kind of sheet-like structure. So similarly with the cobalt molybdenum. So what we understood is molybdenum, whenever molybdenum is present, you started to see the sheet kind of very thin layer and sheet kind of a structure formations happen, and it's also very crystal on the structure. So we thought molybdenum, one of the roles of the molybdenum is to give this sheet like kind of a structure. Okay, and then we studied the activity, evaluated the activity. There are too many curves, please don't worry about it, but I have shown this bar diagram where we have done the activity, measured the activity, that means calculated the over potential at 10 milliamp per centimeter square for all this material. What we found is nickel, cobalt 2, molybdenum shows a better, very good activity compared for both hydrogen evolution as well as this is oxygen evolution and this is hydrogen evolution reaction. So here also you can see that nickel, cobalt 2 and molybdenum shows better activity compared to other materials. Okay, we also did the mass specific activity compared to the mass, and what we found is on a mass specific activity, the cobalt 2 molybdenum shows a better activity compared to, so here also you can see that the cobalt molybdenum here, cobalt molybdenum shows a better activity compared to cobalt nickel, nickel cobalt molybdenum sample. So, but still, if we consider the geometric activity, nickel NiCO2MO shows a better catalytic activity. What we found, when we did various studies, but I'm just in a nutshell, I'll try to explain what we have got it and understand. What we have found is, if we do that, when we do the ICP-AES analysis to understand the different concentrations of this metal post as well as the initial concentration of this metal, what we found is there is an leaching of molybdenum occurs during this both hydrogen evolution, oxygen evolution reaction as well as hydrogen evolution reaction. Here you can see the concentration of the molybdenum matching with the time, it slowly increases in the electrolyte. Okay, so what we said is this from the sample that molybdenum leaching increases. This is something very interesting, which is leads to the activity, because once the molybdenum leaching is happen, it creates a lot of pores in the catalytic material. So what is very important, the electrolyte can now reach out to the bulk of the material instead of only doing on the surface of this catalysis on the surface of this material. We found this is one of the major reasons for better catalytic activity by this material because of the molybdenum leaching, which increases the number of active sites that the electrolyte can reach. So then we did the overall water splitting, as I mentioned before, one of the idea with which we wanted to do the overall water splitting. And here we can see the overall water splitting, which is done in the 2 electrode setup, where both the material is same, but one does the oxygen evolution and the other is for the hydrogen evolution. And here I will show the results in the bar diagram, like the aerial capacitance, which you can see for this material, hydrogen evolution, oxygen evolution. You can see that the increase in the double layer capacitance value, and also before and after, what we have found is, this is before stability, after stability, the activity improves, the over potential basically decreases, as I mentioned before, that there is a leaching of this molybdenum, which increases which decreases the over potential. We have also studied the stability at a long days, for example, 7 days. We have studied that one, like generally people do for 24 or 48 study, but in this case what we have done is basically we did a very long-term stability studies for 7 days, and what we found is that the catalyst is more or less stable, except after the precondition, the catalyst is very stable. Okay. So we have also measured the theoretical and experimental Faradic efficiency. We compared them and we found almost 90% efficiency for the oxygen evolution reaction. Okay. So this study, which led to like whether it's only the molybdenum does this, whether any other anion can also do this one. So we have the immediate example that came to our mind is phosphate. And what we have done is we have prepared cobalt phosphate. Of course, we have prepared different phosphates, and we also doped zinc to this, whether to see how zinc ion, whether it can improve the activity of this cobalt. So this we have done directly on the carbon paper, and what on a carbon paper, and what we found is basically again same, the phosphates along etching happens. But interestingly, in this study, we found that the zinc also leads to some extent on the surface. So basically what happens is during the precondition step, that cyclic voltammetric step, which we do initially, the zinc cobalt phosphate hydrate, which we prepared initially, is converted into oxyhydroxide formation. Okay. So this is what happens in this is you can clearly see that the electrochemical reconstruction of this cobalt phosphate happens like from here, like this is before the precondition and this is after the precondition. That morphology is completely changed, and also this is also supported by the EDAC studies, that there is a decrease in the zinc cobalt to zinc ratio after the precondition step. And what we have done here is again like we have done this concentration we have measured of phosphorus on pure KOH after activation, and then we have studied this ICP analysis for different, like we have done the electrochemical studies, we have taken the sample electrolyte at different time, and we have studied, and what we found is initially there is an increase in the concentration of zinc, but zinc leaching is not much, but compared to the phosphorus, there is a zinc. That means that the phosphate etching happens at the surface. So here I have shown that the activity of this material for the towards oxygen evolution reaction. Here again we compared like the ruthenium oxide, which is, but somehow we found that the ruthenium oxide better, our material is something very close by, particularly at a higher current density. You see this is very close to that of the ruthenium oxide that is used in the commercial this thing. So this is again that the anionic current density, we have calculated the Faraday efficiency, which says the electrochemically active surface area. Again, what we found is the double layer capacitance is very low for only zinc phosphate. Cobalt phosphate is something extent, but particularly zinc cobalt phosphate with the 0.3, that is 30% of zinc, you see that a higher activity. For all zinc dope samples, here, most of these are zinc dope sample, there's only a slight difference in the double layer capacitor. And also you can see that the activity is also very similar. I have not shown here, but its activity is also so similar. So maybe next maybe 5-10 minutes, what I will do is I will skip one of this work, which I just wanted to show that this we have done is on the vanadate. Again, we found something very interesting. We have taken two different vanadates, and what basically happens, what basically happens is one of the vanadate, it depends. So why we took vanadates is because they are a class of oxometalloids which can exist in discrete polymeric units. Okay, for example, VO4 3 minus, in metavanadate is VO3 VO3 minus. So what we found is one is polymeric vanadate VO4 2 minus, and the other one is the metavanadate. So we have prepared this at different synthetic routes. This is just a morphology. I'll just go to the main study to show. You see the activity compared to VO. One is VO4 2 minus, 3 minus, another is VO3 structure. So what we found is whenever there is a polymeric vanadate is present, which is present in this case, CO-V2O6, there is an increase in the activity compared to this metavanadate structure. Later we understood the reason is the polyvanadate is easily leached out because of their structural difference. See, they leach out much compared to the metavanadate sample. This also we have confirmed by making another polyvanadate V2O7 because we couldn't get the pure phase, but which we exist at these two phases. But you can see that the activity improved compared to the metavanadate sample. So very clearly we have shown that if you take the two different vanadate structures, so the leaching is not only dependent on ion, but on their structure, how they have made. Okay, so this is again confirmed from the ICP analysis, what we can, the post-catalytic electrolyte of V2O8, which you can see the vanadium and the cobalt ratio, but here you can see the post for this sample and this sample is like in the electrolyte. So you see a very high concentration, whereas it's a very low concentration. That means here there is a vanadium leaching is there, and here there is no leaching. Okay, whereas the cobalt you see is more or less similar. It's not really much leached out. So cobalt generally doesn't leach out, nickel much not leach out, but the anions leach out, which improves the activity, which is what we wanted to tell this one. Okay, so so we probably with another few minutes, I'll take. Can I take another few minutes?
Yeah. You are just left with another 8 to 9 minutes. You are having.
Oh, 8 to 9 minutes. That's good. Thank you. Thank you so much. I can do this. Then I will not go fast. So this is a study which we recently got accepted, where we recently performed. What we have done is we wanted to make something iron-rich material. So in the literature, so as I mentioned before, that oxyhydroxide is the one which happened during the precondition steps. So mostly it's the cobalt oxyhydroxide or nickel oxyhydroxide samples. So we thought, why don't we make something with the oxyhydroxide? However, our idea is completely if we do nickel oxyhydroxide, the activity might be better, but or cobalt. But the problem is nickel and cobalt, their abundance is very less. We thought if we can see and iron doped materials, iron doped cobalt, iron doped nickel has shown better activity. However, most of the time it's a very small amount of the iron which increases the activity of the sample. So we thought, why don't you make the nickel the other way, whether it will be possible. So in this context, we were trying to prepare like bulk material also, but preparation of oxyhydroxide is not, it's not very easy. It's a little challenging. So we try to prepare this oxyhydroxide as a nanorod. We wanted to make a small structure so that we will have that nickel. If we have even small amount, we wanted them at close to the surface so that the activity can be improved. So what we have done is nickel 6%, only 6% nickel on iron oxyhydroxide nanorods. So what we found is the 6% shows a much better activity compared to the only iron oxyhydroxide sample. So nickel is very much needed for them, but in this case, nickel is only a very small percentage. It's mostly an iron-rich material. So what we have done is the synthesis is quite simple, but it's a little tricky. The conditions have to be very tricky. So what we have done is iron chloride and the nickel chloride we have taken, and PEI is used as a polyethyleneamine is used as a capping agent. So this synthesis works better when we have the polyethyleneamine. Okay, when the absence of polyethyleneamine, it's little complicated. The structure iron oxyhydroxide may not be completely formed. Our pure phase of iron oxyhydroxide is little challenging. So this again, it's only 90 degrees centigrade in 4 hours. You get a beta iron oxyhydroxide nanorods, which I'll show the image, but we have confirm first the phase of this material, which matches with the iron oxyhydroxide phase. And what we observed after nickel doping is slight shift to the lower to higher to theta value. Okay. These are the 10 images of this material. You can see that they are nanorod morphology and they are crystalline as well, which we can find out that the D value and which corresponds to 211 plane. And this is for the nickel iron oxide. I said 0.3. We have made the, we try to reduce whether still can be reduced, but however 6% we found that optimized results. And this is the aspect ratio, the nanorod length is plotted where we have higher rod, but when we have nickel, what we observed is that rod's length of the rod decreases. So basically the rod morphology retains, but we can change the rod with the nickel amount with the same synthetic procedure. And here I have shown that the electrocatalytic activity on the glassy carbon electrode and the carbon paper. So the reason the carbon paper is different because it improves the conductivity, whereas the glassy carbon electrode gives the intrinsic activity of the sample. Okay, so we have compared this glassy carbon as well as the carbon paper activity for all this material, where we have compared that only iron oxyhydroxide and compared with 3% nickel as well as 6% nickel, and 6% nickel I showed is a better catalytic activity, that means lower over potential compared to the other two samples. Whereas iron hydroxide, you can see that it doesn't reach even the 10 milliampere per centimeter square. Similarly here for carbon paper, of course carbon paper the value is slightly better. And then you can see that this shows both nickel 0.3 as well as 0.03 and 0.06 shows better activity compared to the only nickel iron oxyhydroxide samples. Okay. And we have tried to compare with the nickel rich material. So this I mentioned before, that is only 6%. This is, to our knowledge, is the lowest nickel concentration in nickel based material. There are reports 50, 40, 30, up to 30 that people have done, but we have observed only 6% nickel in the iron oxyhydroxide sample. So we've compared with the nickel activity of this material compared to nickel rich material. Nickel rich material, for example, hydroxides, layered double hydroxides are excellent materials for the oxygen evolution reaction. And we try to prepare this nickel rich material, for example, nickel 0.8, iron 0.2, which is HMTA, urea, different bases. So we have compared the results with our nickel 0.06 iron oxyhydroxide material. And what we found is still, compared to nickel rich material, this iron oxide, nickel 0.6 iron oxyhydroxide material shows better activity compared to the nickel rich materials. So we also did the chronopotentiometry to understand the stability of the catalyst, the electrochemical stability of this catalyst for 24 hours, and found that there is initially there is a slight decrease in the potential, and then it basically maintains this. So in the next couple of minutes, I will show you one example of material, interface material, which is used for the alkaline hydrogen evolution. Initially what I discussed, MOS2 is mostly good for the acidic hydrogen evolution reaction. And most of the oxygen evolution reaction happens in alkaline medium, so which is KOH as the electrolyte. So if you wanted to combine the electrolyzer, the commercial electrolyzer, we have to have it in one electrolyte. Okay, basically it is the alkaline electrolyte or the PM, like a proton exchange membrane electrolyte. So what we need is, in a PEM, what we need is a very good material which does acidic OER as well as acidic HER. Acidic OER is again a very challenging thing. And also in the alkaline part, if you see OER, we have different materials, but for getting a hydrogen evolution reaction in the alkaline OH is again a bit challenging. The reason what you can see, for example, the platinum, which is a very good catalyst, which I mentioned before, is very good in the HClO4, in the acidic medium. For example, if you change for example, in the KOH, you see the activity decreases, very much decreases for the platinum 111 surface, which is a very good catalyst for hydrogen evolution in the acidic medium. But when we come to the base, hydroxide medium, or in the alkaline medium, it's not a very good catalyst. So what we need is a material which the reason which we have is because the mechanism is different. I mentioned before that in the acidic the proton is already available. For in the alkaline condition is the water. So we need something, the water dissociation step. So this is the additional barrier in the alkaline hydrogen evolution reaction. So what we need some kind of a promoters which can help in the hydrogen water dissociation step. Then the platinum will take over, or any other material will take over the hydrogen evolution reaction. So in this regard, nickel and cobalt based materials are combined with the platinum, because these two materials can do the water like the dissociation step, and then the platinum does the hydrogen evolution reaction step. So mostly the alkaline hydrogen evolution reaction happens with in the presence of some kind of a promoter. Okay. So we thought our idea is to develop this nickel selenide molybdenum. Selenides, the reason we took selenium is because they have a slightly better conductivity compared to the sulfur analog. Also, when you see the literature, there is relatively very less reports on selenium based materials compared to the sulfur based material, but selenium still shows a better activity. The challenge is mainly because sometimes you have the selenium impurity, which we have observed. Like several syntheses, what we do we get is selenium impurity is present, because reducing selenium is something. Selenium has different oxidation states, so that is also a very challenging thing. So synthetically, it's a little challenging as well, but it is achievable. Okay. So what we have done is this is solvothermal reaction, where we have taken this nickel selenide 0.75 SC, which we characterize using XPS, and what we have done is 20 milligram of this is converted, is added to this added to the molybdenum source for a precursor to get nickel molybdenum selenide interfacial structure. Okay, so what we observed is this 0.75 SC, nickel 0.5 SC, after reacting with the molybdenum, this hydrothermal reaction, what happens is basically it converts into 0.85 SC. Okay, there is a slight phase change which happens during this synthetic process. So which we have confirmed from the XPS as well as XRD measurements. You can see that the composite has both peaks of this, and additionally you can see that this particularly for 0.75 SC you see a small peak in this, but here we do not see that peak that much. Okay, so there is a slight the conversion of 0.75 SC to 0.8 SC, and you can see here this is the XPS spectrum, where you can, I'll put the other one also, it will be easy. So where you can see that 0.75 SC has nickel 2+ concentration, like content less compared to 3+, whereas in the 0.85 SC, this is for the composite, we see there is a difference in this ratio. So basically the 0.85 SC has more nickel 2+, which is also reflected here. Okay, so of course this selenium is something, this surface oxidation is unpreventable. This is also another issue with the selenium, that you have this surface oxidation which you can easily clear from the XPS analysis. And here I have shown the hydrogen HER performance evolution in 1 molar KOH, and you can see here, for example, this is the PTC. We compare with the PTC, and you can see the activity, like for this example, nickel, this nickel composite, which shows a better activity compared to the only nickel selenide or this one. So here we have seen that the overpotential of this material, and this is also reflected the next to the PTC, it is basically the composite, and here you see that the Tafel slope value is much lower compared to the individual thing. So what we need to do is this nickel molybdenum selenide, for example, or the nickel selenide, which shows a lower activity for the hydrogen evolution reaction. So it basically this the composite requires low overpotential compared to the MOSC2, for example. So which clearly indicates that MOSC2 alone is higher compared to the composite. You can see, so it basically improves MOSC2 activity increase when it comes combination with the nickel selenide samples. So this is the oxygen evolution, as I mentioned before, that we have done the oxygen evolution reaction of this material also. And what we found is nickel 0.7 SC is a better catalyst for compared to this one. It still shows activity, but this only nickel selenide has a better activity compared to the composite. So what we have done is to make a like 2 electrode setup, and we wanted to do the overall water splitting. So we combined this composite for the hydrogen evolution reaction in the alkaline medium, and we have compared this nickel 0.7 SC for the oxygen evolution reaction, and this is the overall water splitting reaction. This is the combination, the two overall LSV backward scan, and it shows that 1.7 volt to split water. Okay, so this is here I have shown that the long-term stability of this sample, which is quite stable, and so only slight increase in the potential needed after 24 hours. And we also compare before and after stability, that the values are not really much change except the 15 millivolt difference between them. Okay, so this we do to check that the electrochemical stability of the how robust is the material is. So in summary, what I will try to convince is the preparation of 1T MOS2 and MOS2 is achieved through ionic liquid as well as chromium dope sample, which shows better, both the samples shows better electrocatalytic activity for hydrogen evolution, and nickel nanowires are found to be very good catalyst for oxygen evolution. Then I have shown examples of this tri-component system where nickel, cobalt, molybdate, where we found that higher activity due to the leaching of the molybdate sample, which was extended to vanadate as well as phosphate samples. We have done other samples like silicates also we observed, but I couldn't show the results. And then we observed like how iron-rich nanorods can be. Iron-rich nanorods with a very small amount of nickel incorporation shows better activity compared to the nickel-rich materials. And then we finally have shown some example, just one example that we have done is an interfacial structure formed from between nickel selenide and molybdenum selenium for the alkaline hydrogen evolution reaction. So this none of this work would have be possible without the hard work of my students. So I thank everybody who has contributed, past, present, and students who have contributed to this work, and also the funding sources from DST, SCRB, CSIR, as well as IISER Kolkata for all the facilities and the funding. And thank you all for your patience, particularly Sunday morning. I know how difficult it is. Even I felt I was cursing Rajkumar for a few minutes. And of course, then later I thought it's the morning should start really very early. I understood that. And once again, I thank Professor Saravanan Pichai for the nice introduction, as well as thank the organizer for this giving this opportunity. And I'll be very, very happy to take any questions or comments, suggestions, everything. I'll be very free to take it. Thank you so much.
Thank you, Professor Venkataraman, for your enlightening speech and the comment in that for fuel cell. That's quite interesting. So I now request that participants, you come up with questions. It's a good time. You can just get clarified, or you can just take up suggestions also with him. So can continue with the questions. Yes. Muthu Kumar, who raised your hand, you can just unmute and then you can ask the question.
Am I audible?
Yes, little voice is low, but it's okay. Yeah.
Yes, sir. Actually, you are choosing transition metal as electrocatalyst for HR and OR application.
Yes.
Most probably they are using nickel and cobalt. So why not we can use other transition metal as electrocatalyst? Because if you are using other catalysts, the catalytic activity will improve or not.
So I think it's Muthukumar from SRM.
Yes, sir. Yes, sir. I'm.
How are you? Yeah, good
fine,
to
fine,
see you.
Yeah.
Yes. Good. I'm fine. Thank you. This is a good question. Actually, you should have showed one slide. Like, what is very important today is that we have to think about when you think about a catalyst, two things. One is, of course, activity. We always want better activity. The other thing is the abundance. Okay. So, for example, expensive. For example, cobalt. So I have shown many cobalt-based material, nickel-based material, cobalt is again a very good material, but problem is quite expensive, cobalt, okay, compared to nickel. This is the reason that we have recently started thinking of like how to make like iron-rich materials, okay. But the activity of nickel and cobalt are very good. So next to platinum, of course, still if you ask me, platinum is the best, because you take a platinum wire, put it in water, you started to see these hydrogen bubbles. So because the delta G for this reaction is close to 0, so it will definitely do hydrogen. But platinum is quite expensive. So that is the reason whole this research is going on in iron and like cobalt-based material. But now, not only in batteries, particularly in batteries and other places, the iron-rich material they are trying to see. You have to come up with a material which shows better activity. But if you see for any other alternative, for example, molybdenum, again problem, but it's not quite active. Okay, but if you say rhenium, expensive, you can do. So,
Yes, sir.
but niobium, it may not be very active, but how to make it active? See, for example, if you take a small amount of niobium and put it in iron oxide hydroxide, I'm just saying as an example, we have never tried. If it shows better activity, is fine. So what people have done is they have taken platinum small amount and tried to put it. That shows better activity. Okay, but
Yes.
still, I don't see, we have to try. Sometimes we have to try morphology, activity, as I mentioned, that the surface reconstruction, which is a process which happened during precondition, is also very important. So which gives, it allows that the electrolyte to go inside the material and do this like electrocatalytic activity. So
Yes.
if you have very small amount of even precious, for example, 0.1% of platinum, then still it's better. So it is something which you have to play with. Okay, and of course, what is very important is the stability point of view. So there are many concerns. One is activity, stability, abundance, how you prepare, how stable material, all these things are important. So you have to play with. It's not that it is. See, we never thought that this 6% nickel will show better activity, but we could see. So definitely it would be possible.
Sir, and one more question.
Yes.
Yes, sir. According to Tafel slope, the commercialized electrode like ruthenium oxide and PTC, so lower over potential compared than
Yes.
your material. Then
Yes.
how it is possible to reduce the over potential, sir?
So that's what you have to do this like surface engineering. For example, see the problem with ruthenium oxide and other material, they definitely, as I said, they are benchmark catalysts. Commercially, they are available even ruthenium oxide. But the problem is then oxidation is one of the problems. Okay, but these are tested under the electrolyzer conditions. Okay, commercially, this is a problem. Device, we have to work on device thing. Then we can try to modify the engineering. For example, you have to make little more crystalline the material. Okay, when it goes to the crystalline, the activity decreases. However, we have to do some kind of an engineering so that the material can show close, very close to. So it is not that always we need better than ruthenium oxide. We have to, because ruthenium oxide has some other problem. So we come very close to the ruthenium oxide, which is very important. And the commercial scale, okay, and that is more important. So what we have shown is so far, whatever I have shown, I cannot combine that this will definitely be better in commercial scale. So we have to scale up and see. Okay, so that is one of the biggest challenge also.
Thank you, sir. Thank you very much.
Welcome. Thanks.
Any more questions from the participants?
Yeah.
Yes.
Yeah, I have. I had a very wonderful talk in this session. I have small basic questions
Yes, sure.
for this hydrogen evaluation,
Yeah.
oxygen evaluation reaction. Apart
Yeah.
that, these two reactions I like to know. This is water splitting is giving hydrogen fuels,
Yes,
but we need to do some storage for this hydrogen
very important. That is the
because we are creating we are generating hydrogen, but a problem is how to storage this hydrogen and how this hydrogen to transfer from one place to another place. That is main problem nowadays. Therefore, we need more research on that, right? So
definitely.
just
So,
yeah.
yeah, hydrogen storage itself is a big challenge. Okay, that's why if you see that there are a lot of our Prime Minister Modi also indicated that. So hydrogen mission. So that is a separate thing. So what we need ultimately is sometimes we need to combine research. Okay, ultimately, like you have to make, you need a better catalyst for hydrogen evolution. Then we need a storage material, for example, metal organic framework. So people are trying, but metal organic framework has its own problem of stability, especially in the water condition. So you have to make a very good material or some other materials, storage materials like magnesium-based material. So these have to be made, and that's the thing. Like ultimately, you have to integrate finally. Finally, as I think Professor Saravanan Pichai yesterday told about that, we just simply say that water purification, but there are several steps involved in that. So each step have to be optimized and things like that. So this is basically, as I said, we are decoupling the reactions first. Ultimately, what we need is sunlight, which should be coupled with electrolyzer, and the energy should be stored. So what we need to work, we have to look for the literature particularly. So everybody cannot work on the same thing. For example, we work only on electrocatalyst. So like somebody has to work on photocatalyst. So come up with the best material for hydrogen evolution, and the storage, whoever working on storage, that literature we have to integrate. So ultimately storing the hydrogen is one of the biggest problems. To store them, we can actually use them. So there are, like, for example, metal hydrides are one of the examples where metal hydrides. So we need to think of like how to make a metal hydride in a simple way, like that can be used for, like magnesium-based materials can be used for hydrogen evolution, so that it can store immediately whatever that hydrogen evolution evolved hydrogen and can be used. So I think a long way to go, but one should have a like literature understanding how these related fields are going. I myself should say that I don't have much knowledge, but I know that MOFs, other materials are trying, people are working on it to get a very good hydrogen storage property.
Okay, so I just, if there are no more questions, so I would like to thank Professor Venkataraman Mahalingam for his wonderful speech. Really, it was quite interesting because I also working in microbial field cell, not exactly at this field.
Great.
We
We
also
will.
try to develop the similar kind of and substitute for platinum, same challenge.
Okay.
The only thing is that microbes is going to work as a catalyst here for electron generator. So that's what the context is different, little bit different. But ultimate aim is to get an replacement for an platinum organ.
Yes.
That is what it's quite interesting. So I just like very much.
Thank you so much, and we are close by. We will meet sometime definitely.
Yeah, sure. We should meet.
We should meet definitely. Yeah.
Okay, so I would like to thank on the behalf of the organizers, and I would like to thank for your wonderful speech.
Thank you very much. Thanks a lot.
Thank you very much, sir, both of you.
Thank you.
Thank you for your kind acceptance for this chairperson as well as the
pleasure.
Yes.
Thank you.
Thank you, sir, for your enriching and thoughtful words.